This section of the book is on hydrostatic pressure. It's a very short section, and this lecture won't take very long. As you may guess from the title, hydrostatic, hydro means related to water, static means motionless. The hydrostatic pressure relates to pressure experienced underwater that's not moving. It doesn't matter if the liquid is water. It could be most any liquid as long as we know its weight density, its weight per volume. And I'm going to assume we're on Earth, but you could do this anywhere. Again, you'd need to know the weight density of whatever the liquid is on whatever planet you're on or out in space. I'm also going to assume that air pressure is negligible in these problems. We'll typically have an open body of water, and you could imagine the air pushing down on the water, but we're going to assume that that force is negligible. So how does, there's one more thing I should say, that there are lots of interesting physics aspects to pressure in liquids, and this is not meant to be a physics course, and I'm not going to talk about all the physics involved. It's a cool and interesting topic, how pressure is transmitted through liquids, and I suggest consulting any physics book for more information on this. So suppose you've got, I'm going to say a body of water, but again, it could be essentially any liquid. Pressure, so what we're interested in is pressure on a surface that's, I'm going to write area A and some depth. I'd like to use a little d, but then we'd get confused when we go to integrate and you have a little d for the differential. So I'm going to say the depth is capital D. Then pressure is force per area. So force divided by area. In metric units, so this would typically be, you would look at like 1 Newton per square meter. This has a name. This is called 1 Pascal. In English units, you would typically use a pound per square inch. This is just abbreviated 1 psi. You may have seen psi. Yeah, even though we use lb to abbreviate pounds, when you use pounds per square inch, it's psi. What we're actually going to use today is 1 pound per square foot, and we're just going to call it 1 pound per square foot. So how much pressure in this simple situation where here's some open body of water, this is all meant to be at the same depth, it shouldn't have looked so slanted. I've got some surface with area A. How much pressure acts at each point on this exposed surface? And I'm going to tell you how you can think about it in this setup, but it actually is much more complicated and works more generally. This is just an easy way to think of it. So in this setup, you can think, the pressure that acts at each point on this surface is due to the weight of the water above here. I am most comfortable with English units here, so let me give you the weight density of water. We used it in the last section on when we lifted water out of different kinds of tanks. But the weight density of water, we're going to take it. This is an approximation, and it also depends approximately on the temperature of the water. But we're going to use the weight density of water, delta sub W, and I'm really thinking weight density, but you could also think of that W for water today, is about 62.4 pounds per cubic foot. All right, so what is the weight of all of the water that lies above this surface? Well, you would take the weight density of water and multiply it times the volume. So what is the weight? So what is the volume of this? Well, it's just the area of the base times the height, which is the depth of this surface. So the weight of water above the surface, or the plate, whatever you want to think of it as. The weight of water above the surface is, well, just the weight density of water times the volume of water. And that's the weight density of the water times the volume of the water, just the area of the base times the height, A times D. So this is the weight of water above it. This is force. And then you would divide by area to get the pressure at each point. So the pressure at each point on the surface equals, well, this force, this weight, divided by A. So you just end up with the weight density of water times the depth. All right. Well, that was easy. What's interesting about this? Well, first of all, the pressure varies with the depth. So if we want the total force acting on some vertical plate, then the depth of the vertical plate changes, and so you'll need to do an integral. But even without that, I need to say a couple of more words about why pressure is so cool without explaining it. It's an experimentally verified fact that it doesn't matter how the plate is oriented. Like you could have some object here, some solid object. This is supposed to be a solid object of some weird shape. And what's true is that what's the pressure that acts right here at this point? Even though this has a weird shape and the surface, is kind of tilted, it's not flat, the pressure, the force that acts per square unit there, it acts perpendicular to the surface, so it goes right into the surface. So we say normal to the surface. I don't know why we say normal for perpendicular, but we do. It acts normal to this surface, and its value, the value of the pressure here, is still whatever this depth is. You might think this mass, this solid being in the way, matters, but it doesn't. If this is D, then the pressure, the magnitude, well, the pressure, which is a scalar, the pressure here is still the weight density of the liquid, so the water, times the depth of that point. So that's kind of cool. But pressure is even more interesting than this. You could have a completely, so this is why the simple explanation isn't really all that's going on. You could have a completely sealed container of water, and it's open over here. And the water level, this is all full of water. And you have your plate over here, or a solid object, and we're looking at its surface. You might think, after the explanation I gave for how you could think of where the pressure comes from, that you would just look at the weight of the water directly above the surface. That is not correct. And it's weird, and I'm not going to go into it. It's not a nice, easy integration problem. But it's true that it's still, how much pressure does this experience? And what do you call the depth here? Strangely, I mean, you may think it's strange, but The depth is measured from here. So this is the depth when you're in a strange, like kind of closed container like this, that you take depth measured from this top free part of the surface of the liquid. It's interesting. We're going to pretty much, the problems we're going to be interested in will typically have an open surface to the water above the part that we care about. But it is interesting to know that this is true. One final thing that I should mention, and I'm also not going to go into this because it's a long, interesting discussion that's best done in multivariable calculus. But the fact that the pressure depends on just the depth and acts in all directions explains Archimedes' principle, the principle that the buoyancy force that acts on an object is equal to the weight of the displaced liquid. It's an interesting topic. It's the discovery that supposedly made Archimedes leap out of the bathtub and run through the streets naked yelling "Eureka!" But we're not going to go into that. But that's another interesting physics topic related to hydrostatic pressure. What are we going to do with it? We're just going to look at one type of problem. I'm just going to do one example or two, depending on how you count. What we're going to do with it let me write up here that we're taking the weight density of water to be 62.4 pounds per cubic foot. All right, what are we going to do? We're going to suppose that we have a small dam or maybe a swimming pool, either one, it doesn't matter. Something that I'm going to have something that I'm going to fill up with, or maybe not fill up, but it's going to have water in it. So my perspective is not so good. All right, so what I want to assume is I've got something. So here's something that will hold water. Think of a swimming pool or a small dam. And I'm going to assume that this end, so either this dam or this end of the swimming pool, is parabolic in shape. I'm going to give an equation for it. I'm just going to assume it's y equals x squared. And what I want to look at is, and we'll have some water in here, maybe not up to the top, but some water in here. And our question is, how much force due to the hydrostatic pressure, how much force is this side of the swimming pool or this dam experiencing from the water pushing on it in that direction? So that's our question. I need to actually give some specific numbers. So let's assume that this is a perfect parabola. Here's the y-axis, here's the x-axis. I'm going to assume that I'll set up y equals 0 down here and y equals 9 up here. And this will be y equals x squared. The graph of y equals x squared. Let's assume this is y equals 9. So then this would be at minus 3. This would be at 3. Since I'd like some units, all my units are in feet. So all distances in feet. And I want to look at, I said one or two examples. I'm going to either assume it's full, so that we have water all the way to the top, And then in the other case, I'm going to assume we only have water up to y equals 4. So, and then I want to calculate how much force. So my two questions are, I guess I'll refer to it as a swimming pool instead of a small dam, small water reservoir that's dammed. How much force acts on the parabolic end of the pool when the water in the pool is 9 feet deep and what about when it's 4 feet deep? Okay, compared to some of our problems, this is relatively easy. What's happening here? So you've got this parabola. Let me first do the 9-foot deep situation. So here's y, here's x, and I'm assuming that we have, here's y equals 9. I'm assuming that it's full of water. This is an end view. We're looking from either inside the pool towards this end or from outside the pool back the other way. But since we would like for our force to come out to be positive, I'm going to assume we're looking from inside the pool, and we're talking about the force that the water pushes against the pool with. So I'm going to get positive force because I'm going to say that's the positive direction. All right. So how do you do this? Well, the pressure, the force per area, so the pressure at any point is the force per area. And we know that the pressure at any point is the weight density of water times the depth at that point, the depth of the water at that point. But what's happening is the depth changes as we move down the face of this wall. So what do? Well, you do the infinitesimal problem. So take some y coordinate, which also corresponds to some depth, some y coordinate where you have water. Look at all the points that have the same depth at that y coordinate. Well, that's all the points at that y coordinate. But then we need to thicken it an infinitesimal amount to get some area. So you thicken this. And so here we are at some y coordinate. But then you thicken this to get a little by some infinitesimal change in y dy to get something that has an infinitesimal area. So what do you get then? We're going to take the pressure, multiply times the infinitesimal area, and we'll get the infinitesimal amount of force due to the hydrostatic pressure that acts on this strip. So what we're getting is that the infinitesimal force due to that strip is the pressure, which is force per area, so the pressure, which is force per area, times the infinitesimal area. So this is force per area. You multiply times an infinitesimal little area, and you get the infinitesimal amount of force due to the hydrostatic pressure that acts on it. So we're just going to get that dF, the infinitesimal amount of force from that is the pressure, which is delta sub W times the depth times an infinitesimal amount of area. So that's what we get without putting in what everything is. Of course, we need the depth in terms of y, and we need dA in terms of the y coordinate, and then we'll integrate dF over every y coordinate where we have water, which is from y equals 0 to y equals 9. So that's what we do. So we have that the infinitesimal force that acts at all the points at a certain depth, the depth where you have water, is the weight density of water times the depth of those points times how much area is exposed there, is exposed to the water, in terms of y. So we've got as a function of y, what's the depth? Well, when you're at a fixed y coordinate, so here you are at some y coordinate, then between 0 and 9, the depth is this distance. So distance is y, this distance is 9, so this distance, the depth, in terms of y, is 9 minus y. So what we're getting is that dF is, I'll put in the 62.4, so everything's going to come out. This dF will have force units, pounds. And this is 9 minus whatever the y coordinate is. So for instance, when y is 0, the depth is 9. So that's down here. When y is 9, the depth is 0. Perfect. That's the depth. What's dA? dA is this infinitesimal little area. So it's this length times the infinitesimal height, dy. So I'll just write length in here for now, but it's this length times dy. We need to have an expression for that length in terms of y. Of course, it clearly depends on y. When you're down here, that length is very close to 0, and at the bottom it's 0. At the top, that length is, well, this is minus 3, this is 3. So that length is 6. What is it in terms of y? You have to think about it. It's this x coordinate minus this x coordinate. Well, but this curve is y equals x squared. So if you're given y, what are the two, in terms of y, what are the x coordinates? Well, the negative one, this x coordinate, let me get rid of some dotted lines here. This x coordinate, you're given y. The question is, so what's x? Well, x is plus or minus the square root of y. And this one is minus the square root of y. This one is plus the square root of y. And so this length is this x coordinate minus that x coordinate. So you get the square root of y minus the square root of y. You get 2 times the square root of y for the length. So we get dF equals 62.4 times 9 minus y times 2 times the square root of y times dy. That is the infinitesimal amount of force that acts on this infinitesimally thin strip at y coordinate y. The force due to the water pressure. So what do you do to get the total force that acts on that end of the swimming pool? Add up all the infinitesimal forces every place that we have water, which is from y equals 0 to y equals 9. So now you just take so the total force is you add up all the infinitesimal forces as y goes from 0 to 9. And we just said that that infinitesimal force is 62.4 times 9 minus y times 2 times the square root of y times dy. And this, of course, comes out in pounds. How do you integrate this? So easily. I guess I'll go part way. I'm not sure I'll figure out all the numbers, but the 62.4 and the 2 are constants multiplied times everything. We can pull that out. That is 124.8 times the integral from 0 to 9. How do you integrate 9 minus y times the square root of y? Multiply them together and rewrite the square root of y as y to the 1/2. This is 9y to the 1/2 minus, this is y to the 1 times y to the 1/2. That's y to the 3/2. So you get y to the 3/2 dy. And then you use the power rule twice. 124.8 times, you get 9 y to the 3/2 over 3/2 minus y to the 5/2 over 5/2, evaluated as y goes from 0 to 9. When y is 0, this is 0, so the value that we get is just what we get when we plug in 9. So what you get, and I picked a perfect square so that you really don't have to use a calculator. Most people probably still would, but you don't have to. If you invert the 2/3 and multiply, you get 18/3, so you get 6. So we get 6 times 9 to the 3/2. You can take the square root of 9, that's 3 cubed, that's 27. And then minus, invert this, so minus 2/5 of, you take the square root of 9, that's 3. 3 to the 5th, that's 3 to the 4th, which is 81 times another 3, 243. This is a dot, not decimal. So you get whatever you get. This is still in pounds. I'm not particularly interested in the number that you get, although we could work this out. This is how many pounds of force that water is exerting on that end of the pool. Okay, the only other thing I want to say is, well, what happens if the pool is only filled to a depth of 4 feet? So now I've kind of changed my use of the word depth there. That was kind of what you would say in ordinary English. It's like, in common everyday speech. I mean that you filled this swimming pool, and this distance, the top of the water, is at y equals 4. So what changes? So now I'll just change this to y equals 4. And now we've got water. And yeah, there's some wall of the swimming pool up here, but it doesn't matter. There's no water pressure. There's no water pushing on that. So what we get is exactly what we did in the last problem, or what we did just a minute ago, except now you replace y equals 9 with y equals 4. Of course, that changes some other things. For instance, this is at minus 2. This is at 2. But what does it change in our integral? Well, let's see. We need this infinitesimal amount of force. It's still the weight density times the depth. What's the depth now in terms of the y coordinate? It's 4 minus y. This distance is 4. You're at some y coordinate, y. So this distance is now 4 minus y. I can still write length and dy because we're still going to take these horizontal strips at a given depth. What is the length of that horizontal strip in terms of y? Well, it's still the same thing. It's still the square root of y because, 2 times the square root of y, because this curve hasn't changed. It's still y equals x squared, so the x coordinates are still plus or minus the square root of y. And this is minus the square root of y, and this is plus the square root of y. You still get the same thing. This better be a 4. But your limits of integration, of course, now y just goes from 0 to 4. So all that changes in our integral, but it'll dramatically change the force, I'll let you work that out. Y will go from 0 to 4. Y goes from 0 to 4. And the depth is 4 minus y. But the rest of this doesn't change. And you calculate this new integral the same way you calculated the other integral. You pull out the 2 and the 62.4, multiply this times this, use the power rule twice. I'll let you compare the different forces that you get. This is the kind of problem we're interested in for hydrostatic pressure. It's kind of a simple application of it, just to vertical plates or vertical surfaces inside some body of water or inside some body of some liquid. You really do need multivariable calculus to deal with really more complicated situations, and multivariable calculus does explain from this pressure point of view where Archimedes' principle comes from, but it's not easy. So we'll stop here, and in the next section we'll start completely different topics, no longer applications of integration, but our start of looking at polynomials and infinite series and understanding functions by writing them as like kind of never-ending polynomials.